Welcome everyone to this Europractice webinar. My name is Maria Martinez Balado. I'm a program manager at IMEC and Europractice, and I will be your host today. This is the second episode of the Compound Semiconductor webinar series. We started a couple of weeks ago with an introduction to the compound semiconductor world. We discussed the materials, applications, and market overview. That episode, together with all the webinars that we have done in Europractice, is already uploaded in our YouTube channel. So I invite to all of you to go there after this webinar and check your favorite episodes. So after this introduction I was just mentioning, the rest of the episode of the series, as you can see in the slide, will be each dedicated to a specific material. Today, we will take a deep dive into the world of silicon carbide, and we will put special focus onto its application for devices operating in harsh environments. And then next year, after a Christmas break, we will have episodes dedicated to silicon germanium, gallium arsenide, gallium nitride, and we will finalize the series with an episode on indium phosphide. So, after this short summary of the series, let me now introduce our great speaker of today, Mathias, who is already with us in the session. So Dr. Mathias Rommel is an electrical engineer with a diploma from University of Erlangen and master's from the University of Oldenburg, both in Germany. He got his PhD from the University of Erlangen in 2007, specializing in carrier lifetime spectroscopy and oxide characterization. Mathias has an extensive experience in teaching and research, particularly in contamination and control of electrical device characterization. And then he joined Fraunhofer IISB already in 2002 as responsible of the nanotechniques group and conducting research on nanopatterning, nanoimprint lithography, and electrical scanning probe microscopy techniques for the characterization of high K layers and semiconductor materials. In recent years, Mathias has focused on the in-depth characterization of defects in 4H silicon carbide, and since 2021, he has been involved in high-temperature silicon carbide CMOS activities at IISB. So with this, I have concluded everything I wanted to say, and it's time for me to pass the baton to Mathias. I wish you all a very, very nice webinar, and Mathias, when you want, the floor is yours.
Thanks a lot. First of all, thanks for this kind introduction and the overview of the whole series. So as you mentioned, we will talk today about the 4H silicon carbide CMOS technology and with main focus on high temperature environments and applications. But as mentioned here, of course, 4H silicon carbide is also a good material to work in generally in harsh environments. This is a big reason why I put Alexander here, because he is not only supporting, but he is maybe, especially with respect to the technology, the heart of our technology, so to say. He's also joining. So if you also later have in-depth questions regarding the technology, he can also support me if I might not be able to answer specific questions. As Maria pointed out in the first talk, you already heard a lot about silicon carbide for power devices, for the main market of today, also the whole silicon carbide value chain, silicon carbide wafering, and so on. But I still want to start with one slide about the, how to say, the history of silicon carbide, because to be honest, I was also surprised when I read that silicon carbide was kind of invented or found first time in 1824. And already at the end of the 19th century, a process was developed industrially to grow silicon carbide, which at that time was called carborundum. And yeah, as mentioned here, this process for growing silicon carbide was already patented in 1897, and devices were available around that time already, and in the beginning of the 20th century, mainly for radio detection. So this was quite surprising for me, and that's why I thought maybe it's an icebreaker to show this kind of crystal first, and it might also remind us on the time where we are currently, so approaching Christmas and St. Nicholas Day today, so maybe it's a nice shiny image to show. But from now on we will keep on and focus on technical things. Still though, I would like to start with a slide with a lot of information, but it compares away silicon technology with silicon carbide technology here. And why do I show this? Because first of all, we will see through the whole webinar that we have quite similarities between silicon and silicon carbide technology. But of course, as you might see, and as you all know, silicon technology and devices started in the 1960s around, and mainly with bipolar circuits. But let's say the silicon CMOS circuits and technology started or became very important from the 1980s on until now. We are here, what we talk about today. So it's we are 40 years behind, so to say, but of course that's only partly true. But that's just to show that we have kind of similar devices, similar concepts working on both in power as in logic or analog circuits, but just several decades behind. That's of course mainly due to the material issues and of course other issues as well. We come to this maybe later on. Still, I would like to show some comparison between 4H silicon carbide here in light blue, silicon and gallium nitride, which you already heard of again in the first talk given by Ahmed. So especially for power devices, we have several parameters which are most important, like the critical electrical field the material can withstand, the band gap, the saturation velocity of the carriers, melting point is partly important, but also the thermal conductivity, which is very high for silicon carbide, which makes it ideal also for high power systems. But what I want to focus on are a few things which are related to high temperature operation, because about high power you heard enough. One thing, and that's where I come to in the next image in more detail, is the very high band gap of 4H silicon compared to silicon. 4H silicon carbide, sorry, compared to silicon, and also the thermal conductivity, which I mentioned before. But let's focus on the band gap, because this is very important. What can you see here? It's the intrinsic carrier concentration, which just depends on the band gap and the temperature. There you can see that, for example, for silicon, you achieve an intrinsic carrier concentration of 10 to the power of 15 already at around 200, 250 degrees C. That's why you cannot get any efficient doping anymore at these temperatures. And that's why also the very high temperature applications for silicon just rely on fully depleted SOI and not standard silicon technology anymore. If we, however, look at the 4H silicon carbide here in light blue, you can see that we reach this level of intrinsic carriers just at very, very high temperatures above 700, 800 degrees Celsius. And that's why, for example, if we go to 600 degrees Celsius, which we aim at, you still have very, very low intrinsic carrier concentration. And that's why you can, in principle, just from the basic material, semiconductor material point of view, you can use this material for very high temperature applications. What could this be? What could these be, these harsh environment application fields? Of course, there are many, many of them, but let's focus on let's say, general things like, of course, you have in many industries very high temperatures, like also energy applications or in chemistry. But if we, for example, just have a specific look at sensing at elevated temperatures, we find and figured out together with a partner of us several, let's say, general fields of applications like in geothermal, oil and gas, industrial gas turbines, aircraft engines, automotive engines, and all this stuff with some, let's say, typical temperatures where you might need sensing together with data compression or data acquisition and also transmission, so that you need maybe some fundamental circuits or even more complex circuits for just getting the data out and improving it and amplifying it and so on. So that's one of the applications fields where we also work on by our own, but what we also can offer, of course, for customers. If we talk about circuits operating at high temperatures using 4H silicon carbide, we do have, of course, different approaches which have been published and worked on partly since many years. So one is, of course, the CMOS we are talking about during this webinar. So this is just a cross-section through a standard CMOS inverter, but I will come to this later on. It's just to say that we have here a real pure CMOS technology. There is another one also quite famous from Sweden, from where they work on bipolar junction transistors, and they have shown that they can also operate very good and very stable at very high temperatures. And the third one, which is at least as very well known, it's junction field effect transistor, JFET technology from NASA in the US. And they are also, of course, very famous and have shown reliable and reproducible operation at very high temperatures. The advantage, on the other hand, using CMOS is that, let's say, people who are used to design in silicon or just are generally designers, they are, of course, much more, experienced in using a CMOS technology in general, and that might, simplify changing from silicon to silicon carbide compared to using bipolar junction transistors or JFET topology. Now, very few words to Fraunhofer and our institute. Fraunhofer Institute, as you might know, they are all over Germany. We have 72 institutes in total, and we are located here in Germany. And I just have to mention that some of you might know that Fraunhofer IISB is also a Europractice partner as IMEC is, but it's a different institute, just to mention that. So we are a smaller institute, very close to the IISB, but we are here in Erlangen. And we have a number of staff of approximately 350, including university. And what I have to mention here is, of course, that we are still a non-profit association. On the other hand, our mission is application-oriented research and development. So we collaborate with many different customers or partners. And it has to be mentioned that, of course, we don't have a production line like 24 hours, 7 days, but we just have kind of prototype fabrication line. This is our institute, just to show you, and what I want to emphasize here in this, with this slide and with this picture, that that these buildings are from the University of Erlangen, and we have very close cooperation with the Chair of Electron Devices here and with other chairs from the university. And this chair is also headed by the head of our, or the director of our institute, Professor Schulze. So we can also integrate basic and applied research across these two institutions. Good. Second last slide for our institute, just to show that we work basically on the whole value chain of from materials to power electronic applications. If we look at silicon carbide, we don't do the crystal growth, but we start from epitaxy, then go to device manufacturing, some kind of integration. We also integrate silicon carbide devices in electronic systems, like for vehicle electronics, also aviation, and also big energy electronic transmission systems and so on. All this is kind of supported by a modeling and artificial intelligence department at our institute. Last slide. What do we have? We have a full silicon CMOS process chain as well as a full silicon carbide CMOS process chain operated in one clean room, and that's what I somehow indicated already before, that we can use a lot of equipment and also even processes for both technologies. But of course, if it goes to, let's say, annealing or activation of the doping, of course, we need quite different temperatures if we operate silicon carbide or if we operate silicon. But in principle, we can use the same clean room. What might also be interesting that we can, if we work together with partners, like let it be customers or academia, then of course we can already put pre-processed wafers into our processing line, or we can start from scratch, or we even do just first steps and then send the wafers to customers. So very flexible approach to work together with partners. If we look at our portfolio regarding silicon carbide, we basically cover, of course, the power part, like vertical power MOSFETs, trench MOSFETs, JBS diodes, even JFET-based DC breakers. But today, of course, we will focus on our lateral high temperature CMOS logic, which can even integrate smart power. And as I mentioned before, sensing might be very important at high temperature. So we also have UV diodes and sensors. Okay, that was mainly the introduction motivation. Let's now come to the actual process flow. And that means the technology which is available via Europractice. We will now focus on the process flow. I will talk a few words on the process development, which we are currently doing and which we are targeting for, some results, and which might be quite, how to say, motivating, what partners already achieved using our technology, and finally also some words on the access via Europractice. Let's start with the process flow, and I will now very briefly go step by step through the main process steps we need, and also talk a few words on why some steps are necessary or not. Let's start with the epitaxy. You might have heard in the last talk that the silicon carbide substrates, which are below this here, where you don't see it, they still don't have the quality which we need to fabricate devices. That's why we need an epitaxial layer, and that's a very standard epi layer. We have an n-type buffer and then an n-type epi layer on top of the substrate. Then we do the doping by ion implantation and further high temperature annealing. We have basically all the NMOS in an P-well, and here it's not very well visible maybe, but the PMOS in an N-well, and you also have the according contacts for the body and also for the main transistor here. Then we have an oxide which defines the active area. Then we get the gate oxidation. Still at the current stage, we use a thermal oxide here, a thermal silicon dioxide. We deposit the polysilicon, which we use as a gate electrode. It's a highly doped, typically a highly n-doped polysilicon. We cover this with an insulation oxide and then open the contacts. And that's also specific to silicon carbide, at least for our process. We use different ohmic contacts for P and for N-type layers. And we start here in this case with a P-type metallization, which later on will be annealed and forms then the ohmic contact. Second, we deposit the N metal, or the metal for the N-type ohmic contact. And now just keep in mind this picture. This is visible here now. And we just also show now the top view for this structure, for this inverter. Here you can see the NMOS transistor. Here you see the PMOS transistor. And here you see the gate for both of them with the poly. And we have a second cross section here, which is seen here. Keep this in mind. We don't now show the openings through the insulation layer so that we can contact the polysilicon, which is now shown again here in this single cross section. After that, we deposit the first and structure the first metal. And in our case, to achieve high temperature operation, we so far use a platinum-based first and second metallization. Next, intermetal insulation, second metal, and finally a passivation, which of course has to be opened to get access to the metal 2 layer. But that's all a very standard kind of CMOS in terms of the process compared to silicon in the early years. And here again, you have the top view and also the cross section through the, let's say, active transistor area. Okay, now that's basically the process flow. And a very few words on process development, what we already did and what we aim at. And I start with a picture where we show the threshold voltage dependence on temperature, or the threshold voltage evolution of NMOS transistors and PMOS transistors with temperature. In both cases, we get a smaller threshold voltage with temperature increasing. And as you can see here, for example, for the NMOS at 500 degrees, you get relatively small threshold voltages. And also the difference between the NMOS threshold voltages and the PMOS threshold voltages are relatively big, which is due to the material and some other issues. I will not go into detail in this presentation here. But for example, if we use p-doped, highly p-doped polysilicon, we can get, let's say, threshold voltages which are closer to each other. And that's something which is, of course, wanted in principle. And we are still working on this to improve this further. Maybe in this context, I can also show the breakdown voltages of our oxides we use. So as you can see, we start again with the N-type polysilicon. It's both around 60 volts for both transistors or for both MOS structures, like polysilicon on oxide on silicon carbide, in this case highly p-doped, and here highly n-doped. Both show very similar behavior, and it's relatively small influence for the breakdown voltages for the different temperatures. If we now have a look at the p-doped polysilicon, we basically get a similar trend with a slightly even less change in the breakdown voltages, but not anymore that symmetric. So that's something we are still working on. And of course, we have, as we are early access technology, that has to be mentioned as well. We still have a lot of, how to say, screws to work with to improve our performance of the transistors and the technology. Also to integrate more components like temperature, UV, pressure, or magnetic field sensors. Temperature and UV is already common and also from our partners frequently done. We also have the option to integrate smart power devices like or power devices to achieve smart power systems. Here specifically we work with lateral DMOS transistors and not vertical so far. That's something we can of course also collaborate with partners, but not within the frame of Europractice. Of course, one of the major issues should and is high temperature reliability, which should also be achieved by optimized technology, and we are still, of course, improving this. Secondly, we are also aware that, of course, the high temperature assembly or interconnect technologies should be available also for packaging to basically get full systems or not only chips, but also electric systems working and operating at high temperature. As you see, this is just on one slide, but if you know about technology, you know that all this is, of course, a lot of work and challenging, but of course also quite interesting to do research on. Yeah, characterization is just to show you some results with our transistors and inverter. So basically here it's transfer and output characteristics of our transistors. Here with on the left hand is always a PMOS transistor, also here, and on the right hand we see an NMOS transistor. The numbers here, the 80 and 6, are refer to the width and length of the channel. So what you can see and what we also saw from the slide I showed before, where we saw the threshold voltage dependence on temperature, with increasing temperature, you basically get smaller threshold voltages and overall higher currents, which you can also see here in the output characteristics. And yeah, that's something we see here both for PMOS and NMOS. So that's also something which is not the same as for silicon, because we have different mobility effects or models which dominate the carrier transport here. Another example is an inverter with these two transistors I showed before. And yeah, you can see you get basically a very nice transition, but of course also not stable with or identical with temperature. And this kind of more strange transfer characteristics for room temperature is due to the fact that at these temperatures the PMOS is still not fully open, and at this voltages, and that's also why at least the PMOS is it's even good to operate it at higher temperatures and not at room temperature. But of course it still works and gives at least a decent voltage transfer characteristics. And of course one can also optimize it for room temperature conditions with different geometries. Another thing we started working on together with a other Fraunhofer Institute is some more decent reliability tests. In this case, bias temperature instability tests, which are one of the, how to say, investigated issues, especially for edge silicon carbide MOSFETs. And we can see that at least the NMOS is, relatively small change and small instability, and it's also relatively similar to what is shown and expected from silicon. And for the PMOS, we also have a slight threshold voltage shift, but also a slight reduction in the drain current, but it's still acceptable and also not that far off from what is known from silicon in principle. Let us now go to the what we called here technology platform. Basically, as I mentioned before, I will say a few words on what has been shown and achieved by partners with our technology. So we start with single devices which were designed and realized with our technology by the University of Arkansas. So they showed some lateral bipolar junction transistor output characteristics. Of course, they are not, how to say, ideal in the sense of their characteristics, but if you just want to use it for example, band gap references and so on, that's possible using such bipolar transistors. Besides, they used or they realized also a lateral DMOS for kind of power with breakdown at around 180 volts. Of course, you cannot compare it to the voltage classes you heard for the power, the dedicated discrete power MOSFETs, which are realized also at our place for silicon carbide, which are of course available up to 6.5 kilovolts or even higher in these days. But that's something of their design. We are currently trying and realizing LDMOS transistors with much higher breakdown voltages. Finally, what they also realized and designed is a gate driver design in our technology for this, as mentioned here, it's a 5x5 millimeter chip, and they could drive several amperes for a power module. So that is some results from the University of Arkansas. We now show results from the University of Delft. And in one of their first works, again realized in our technology, they just realized several, let's say, standard digital and analog circuit blocks, among them analog to digital converter, NAND or NOR gates, flip-flops, SRAMs, comparators, source followers, and even more. You can have a look here in this reference. But I just want to show one, of course, relatively simple ADC. It's a 2-bit ADC, but they also characterized it very detailed at different temperatures, compared it to ideal behavior and all this. So it might give you also an idea on how accurately you can predict and design your circuits using the technology. And here you can see the 4 bits depending on the, let's say, reference voltage. Temperature sensors are one of the most important sensors we also want to realize. They did realize a temperature sensor with a relatively constant change of the, let's say, their characteristics over temperature, and here really from room temperature up to 600 degrees C, what we also aim at as the maximum operating temperature for our technology. And that was quite linear behavior, so that's something you can realize with this technology. But you can go, of course, much more complex, And this is maybe the nice example what you can achieve here. So in this case, this is a 10 by 10 millimeter chip with all the processing units to how to say drive or use this 8 by 8 pixel array of UV sensors. And with this 64 pixel UV sensor, you can basically locate UV sources. That was, let's say, the main idea behind. But to achieve that, they also did all the readout and control and data processing circuits around it. And in total, it was used more than 1,250 operating transistors, and they had a quite decent yield for those chips here. Okay, let's go to Europractice. What can you get and what do we have? So just to give you an idea of the cycle, so the timeline, the next one will be the second official run with a fab-in scheduled for March of 2024. So there's still some time to apply or register for it. Basically, after the tape out, or let's say from fab in to fab out, it takes approximately 9 months with our technology, with the restrictions we have in the processing. This is just to give you an idea about it. What do we offer together with within the PDK we have, which is, it has to be highlighted here. It's a preliminary version. So what we have so far are, of course, the layer informations, design rules, and some implantation profiles, which you might need to know to design your own devices in more detail. We do a design rule check, or we provide design rule check. This is with K-layout open source software. Layout versus schematic can be done in Cadence Virtuoso, and also we have this P-cell data here. Of course, we also have compact models. In this case, Verilog A models for the MOSFETs, but also we can also use different syntax. What we are currently working on is to extend the PDK functionality, especially for the compact models, which are currently just available up to 300 degrees, but we want to extend it to 500 degrees C, as we have now much more measurement data for this temperature range. We have to work on compact models and P-cells on passives, parasitics, and so on. Yeah, and we also target the detailed TCAD modeling of transistors to better understand and to optimize our further development. Optional process modules exist. If you have later on also questions to this, please ask. We have this RESURF ion implantation, which is important for the lateral DMOS power transistors. We have a dedicated UV module, which is for the fabrication of UV diodes. You can get custom implantations. You can also use aluminum metallization rather than platinum, and some other which are more for dedicated specific requests. Let me come to the outlook and very short summary. As I mentioned, we are research institute, and thus we are highly interested in partnerships and try to build up even ever-growing kind of environment here. So far, the technology development is in our hands. That's something we could, of course, also discuss if someone is interested in supporting or collaborating here with us. It's already quite different if we talk about PDK, P-cells, IC or IP blocks in this regime, or overall circuit design. Here we collaborate also internationally. with the University of Salerno, and I saw, Nicola, you are at least in here, so hi, from also on this side. We work together with the university in India, in Chile, and also together with university in Erlangen, and most of all, as you already saw, also with the Technical University of Delft in the Netherlands. If we come to demonstrators, of course, it's here, what I showed before, also the University of Arkansas, and also another university in Hanover. If we talk about reliability, we have a collaboration with another Fraunhofer Institute, and finally, with the marketing, we also work together with a company here close by in Erlangen. If we talk about marketing, I can announce that we target a design contest via Europractice, which will take place next year, and it's planned for second quarter of 2024. What is the main idea? So you can win free chip area for your designs to realize them in our technology. And what will be, let's say, the aim of the contest is to that you design dedicated standard cells, which then can be used by us for our PDK cell library. And the main focus and maybe novelty will be on the fact that you should try to make them as temperature stable as possible. And if someone is interested in this design contest and want to join, please, you can also contact us later or just send me an email. That would be quite nice. Summary, last slide. What did I try to show? And I hope you could follow it. So I try to motivate why silicon carbide might be a very good material to use for high temperature circuits, and of course also sensing. I gave an idea on the areas of application which might be interesting for these high temperature circuits, but maybe you have already something else in mind, so we are also open to discuss that. I talked about our technology by going step by step through the main process steps for our CMOS. I showed some application examples, and also try to motivate you to become partners or at least take part maybe in the design. Thank you for your attention, and just this is something which you might have got from the talk from the first talk from Ahmed, but what I tried to show you that silicon carbide is also hotter than other materials, and that's why I want to, with what I want to disclose this talk. Thanks a lot.